While, modern infrastructure tends to crumble after just a few decades, Civil War-era telegraph poles are, surprisingly, still standing tall across the American landscape. These aren't just ordinary pieces of wood. They're actually chemical marvels, engineered to be, well, almost immortal. So, how did 19th century soldiers manage to turn rotting timber into iron that can survive for 160 years? Welcome to the Survival Bunker. This is where we study the brutal reality of surviving war zones, sieges, and, battlefield collapse. Today we're not examining a weapon or a fortification. Instead, we're examining a pole, a chemically transformed, copper-saturated timber mass that has somehow outlasted the war that built it, the army that deployed it, and, honestly, just about every other wooden structure erected in the same decade. The Civil War copper vitriol telegraph pole is, without a doubt, one of the most understudied feats of wartime materials engineering in American history. And the reason several of them are still standing is definitely not an accident. It's chemistry. When the Civil War began in April 1861, the telegraph was, by far, the most strategically critical communication technology that either side possessed. For the very first time in military history, a commanding general could transmit orders across hundreds of miles in mere minutes rather than days. President Lincoln actually used the War Department telegraph office in Washington as a kind of direct command interface, visiting it repeatedly to receive battlefield dispatches in real time. The Union's military telegraph corps eventually operated over 15,000 miles of telegraph line by the war's end. The structural problem was immediate and, well, honestly, quite severe. Telegraph poles in the 1860s were cut from whatever timber was locally available, predominantly pine, spruce, and cedar across the Eastern Theater, and a mix of hardwoods and softwoods in the southern campaigns. Untreated timber in ground contact begins to decay through a combination of fungal attack, moisture penetration, and insect activity. In the temperate north, an untreated pine pole in ground contact would begin showing structural degradation within 2 to 3 years. In the humid, insect-heavy swamps and bottomlands of Virginia, Tennessee, Georgia, and the Carolinas, primary theaters of the war's most intensive campaigning. That timeline compressed dramatically. Untreated poles in wet southern soil were failing in under 12 months. The operational consequence was, well, frankly, critical. A snapped or rotted telegraph pole did not just interrupt communication, it created a gap that enemy forces could exploit. Union commanders coordinating multi-corps maneuvers across hundreds of miles depended on continuous wire integrity. Confederate cavalry raiders, particularly units under Nathan Bedford Forrest and John Hunt Morgan, systematically targeted telegraph lines as a primary disruption tactic. A line already weakened by rot required significantly less effort to destroy, and honestly, significantly more effort to repair. The infrastructure was failing faster than it could be maintained under combat conditions. Military engineers needed a solution that could be applied at scale using materials available in the 1860s that would extend pole life from months to years, preferably without requiring specialist knowledge to apply in the field. The chemical answer came from a compound that had been used in European agriculture, mining, and dyeing for centuries, copper sulfate, known in the 19th century as blue vitriol, or bluestone. Its characteristic deep blue crystalline form made it immediately recognizable, and its toxic properties relative to biological organisms were well documented in existing literature. Copper sulfate, chemical formula QSO4, functions as a broad-spectrum biocide. Its mechanism of action against wood-decaying fungi is precise. Copper ions bind to enzyme systems within fungal cells, disrupting metabolic function and preventing the organisms from producing the cellulase, enzymes they require to digest wood fiber. Without cellulase production, wood rot fungi cannot feed. The wood does not decay. The compound's affinity for cellulose, the structural polymer forming wood fiber, was the critical engineering property. Copper ions bond to the hydroxyl groups present on cellulose chains, creating a stable copper-cellulose complex within the wood matrix. This is not a surface coating that weathers away, it is a chemical integration with the wood's own molecular structure. Once bound, the copper cannot be leached out by rain, groundwater, or the metabolic processes of organisms attempting to consume the wood. The timber is not protected by the copper. It is, at the molecular level, partially converted to a copper-bearing composite material. The decision to use copper sulfate for telegraph pole preservation drew on existing precedent. John Howard Kyan's kyanizing process, patented in Britain in 1832, had demonstrated copper sulfate's effectiveness as a timber preservative. The process had been applied to railway sleepers in Britain and Europe throughout the 1840s and 50s with documented success. American military engineers, drawing on this knowledge base, adapted the process for field-scale application under wartime production pressure. The application method was the determining factor in treatment depth and long-term effectiveness. Simply painting copper sulfate solution onto the surface of a timber pole produces superficial penetration, adequate for above-ground exposure, but inadequate for the ground contact zone where biological and moisture attack is most intense. The Civil War-era treatment process used thermal pressure impregnation, boiling the logs in large vats of concentrated copper sulfate solution. The physics of this process exploited two mechanisms simultaneously. First, heat drives out the residual moisture and sap present in the wood. Green timber contains significant water and dissolved organic compounds within its cell structure. Boiling in copper sulfate solution creates a vapor pressure differential that forces these internal fluids out of the wood as steam, creating a partial vacuum within the cell structure as the wood cools. Second, as the wood cools in the copper sulfate bath, atmospheric pressure drives the surrounding solution into the evacuated cell structure to fill the void. The copper sulfate penetrates not just the surface cells, but the deep grain of the timber, reaching the heartwood that is normally inaccessible to surface treatment. The result of this exchange was a structural transformation at the cellular level. Wood cell walls that had previously contained sap and moisture now contained crystallized copper sulfate deposits. The cellulose matrix of the cell walls had formed stable bonds with copper ions throughout the treatment depth. Fungal organisms attempting to colonize this material encountered copper concentrations at every point of contact, not just at the surface, and could not establish a viable colony. The visual evidence of successful treatment was the characteristic blue-green tint that penetrated through the cross-section of a treated pole. A pole inadequately treated showed color only at the surface. A fully impregnated pole showed consistent blue-green coloration to the core when cut. Field inspectors used cross-sectional cuts to verify treatment depth before poles were accepted for installation. The treated poles were not indestructible. Mechanical damage, like artillery fire, storms, or just plain physical impact, could still break them. But, biological decay, which was the main way untreated timber failed out in the field, was effectively eliminated for a treatment depth that, modern laboratory analysis of surviving specimens confirms still contains measurable copper concentrations even after 160 years of ground exposure. The operational impact of the copper vitriol treatment program was documented in Union military telegraph corps records throughout the war. Treated poles along the major communication corridors, the United States military railroad telegraph lines running from Washington through Virginia, and the lines supporting Sherman's campaigns through Georgia and the Carolinas demonstrated service life that dramatically exceeded untreated infrastructure in identical environments. The poles endured conditions that destroyed conventional wooden structures routinely. Artillery bombardment during the Siege of Petersburg, which lasted from June 1864 to March 1865, destroyed significant sections of wire and some poles through direct impact, but surrounding treated poles remained structurally sound despite sustained vibration and blast overpressure. Raiding parties that cut wire found that removing copper-treated poles required more effort than cutting untreated timber. The copper impregnation increased wood density and hardness alongside its biological resistance. Confederate raiding operations under Forrest and Morgan remained effective at cutting wire, but, the structural integrity of treated poles meant that repair crews could often just re-string wire on standing poles rather than having to replace the poles themselves, which really reduced both repair time and material requirements. The U.S. military Telegraph Corps, operating under Anson Steger as general superintendent, actually logged repair times and material consumption throughout the war. Lines supported by treated pole infrastructure showed measurably lower repair rates per mile than lines using untreated timber. The communication continuity this enabled, it had direct strategic consequences. Sherman's March to the Sea, launched in November 1864, relied on telegraph communication for coordination with Grant in Virginia and with the War Department in Washington. The infrastructure that supported those communications had been engineered to survive the southern environment in a way that untreated timber simply could not. Modern materials analysis of surviving Civil War-era treated poles, located primarily in rural sections of Virginia, Tennessee, and Georgia, where original line routes have not been developed, confirms copper concentrations in ground contact wood that remain biologically active. Samples analyzed by historical preservation researchers show copper levels measured in thousands of parts per million in the heartwood of poles that have been in ground contact since the 1860s. These poles are not museum pieces. Several are still standing in their original installation positions, supporting no wire but structurally intact, identifiable by the characteristic blue-green tint of their grain and the preservation records of local historical societies. They are the oldest continuously standing wooden infrastructure in the regions where they exist, outlasting every barn, fence post, and building constructed from untreated timber in the same period. The Civil War copper vitriol treatment program is really the direct historical ancestor of modern pressure-treated lumber. The chromated copper arsenate treatment that became standard in 20th century construction timber uses, the same core principle, forcing copper compounds into the deep grain of wood under pressure to create a biologically hostile material matrix. The chemistry, of course, has been refined. The arsenate component phased out in favor of safer copper complexes for residential use, and the application equipment modernized. But the engineering logic is unchanged from what Union military engineers applied in boiling vats in Virginia in 1862. The enduring lesson from the Civil War telegraph pole is not about wood or copper. It's really about the relationship between material science and strategic outcome. The Union's ability to maintain communication across a continental theater of war depended on infrastructure that could survive the environment it operated in. The copper vitriol treatment program solved that problem with 19th century chemistry applied at industrial scale under wartime pressure, and produced results that have honestly lasted longer than the civilization that built them. These poles are still standing because someone in 1862 understood chemistry precisely enough to make a biological problem into a materials problem and solved it. They did not have modern analytical instruments. They did not have electron microscopes to visualize copper bonding to cellulose. What they had was documented precedent, available chemistry, and a strategic requirement that could not be met with rotting timber. That, in essence, is what wartime engineering looks like when it works. If this briefing changed how you think about the chemistry behind historical survival infrastructure, subscribe to the Survival Bunker and share this video. Every share puts this research in front of someone who takes military history seriously. Hit the notification bell and we will see you at the next briefing.